in case anybody has to watch this later, which it looks like a few people will. We're going to be using Wiley Plus in the fall. It'll be integrated into Canvas. And along those lines, I wanted to tell you guys that the Wiley Plus that we're using this semester in the spring, which was provided for free from Wiley to basically like reel us in, right? So that we would pay for it in the fall. But I think it's worth it. I think it's good. I think it's a really nice resource actually, and we're going to really get the hang of it by the time we get to fall. I hope in terms of using all of the resources, the adaptive practice and the quizzes and stuff. But for this semester, the free version that they gave us for this semester expires on Monday. I just got an email today, and I'm sure they told me this when I first signed up for it, but I didn't care. I wasn't caring about that at that point. I just wanted to get you guys something online ASAP, so I didn't pay attention. Apparently the expiration date is Monday, which is the 25th. It's Memorial Day. So you will have this weekend to use your Wiley Plus resources to study for your final. And the only stuff really that's there, besides the e-text, which wasn't something that, hope you guys already had a textbook of some sort before we had this. The only things that you will be missing out on after Monday will be the, like this kind of stuff. The like, I don't know if you've been using these, but you've got your little interactivities and your adaptive practice and your quizzes and stuff for the special senses. So once again, I am away from my router and we'll find out if that's going to be an issue. But since he's working on my husband's working on our washing machine, not my washing machine. I'm not the little housewife. We both do laundry in this household. But he's making a lot of noise. So this kind of stuff, make sure if you use it this weekend, because you're going to lose access to it on Monday, apparently. So cutting it really close, the timing could not really be more perfect, really. It could have been more of an inconvenience, but I'd want you guys to know for sure that if you're going to be using the Wiley Plus stuff to study for your finals, use it this weekend and, take screenshots or whatever you want to do to try and hold on to some of this info because you're going to lose access to that on Monday, apparently. It is what it is. It was a free version. It was super helpful. It got us through the semester. I'm grateful to have had it at all. So I'm not complaining. Oh, and
Professor.
Yeah.
Sorry. If let's say we do go online, or we do go back in fall and do all this.
Yeah.
Then do we have priority for the second part of your class?
That is also an excellent question that I will bring up because I have never.
It's gonna be so hard even just to get anything.
I know. Since I've never taught the second half, I've never taught 50B before. But what it seems like is the people who teach both, I don't know how they work this out, but it seems like they carry over the same students from A to B. And when I talked to Dr. Gutierrez about it, and this was months ago before all of this went down, and I asked, like, I would like to teach 50B because I'd like to carry my students through. She's like, oh yeah, that's fine. Like, we do that all the time. So she made it sound like it's a thing. I'm not sure exactly how it's going to work. I don't think it's going to be an issue in terms of like limiting class size, and there's not going to be a bunch of people unless people are like jumping ship from instructor to instructor. Like if you guys decided that you hated like having me as an instructor this semester and you were trying to get into somebody else's part B, I could see that being an issue, but like obviously it's just the people that took part A who are going on to part B, right? Unless people from, I guess, other colleges might be coming in and it might fulfill some requirement, but that's probably a rare case. So I don't see there being some sort of big flood of people all vying for a lower number of seats. I think they're gonna still try and keep the same number of students. They're not gonna let some of you move on to part B and not let others of you move on. Worst case scenario, you'll get stuck with another instructor. I guess that could happen, but But it really seems like what they're doing is they're just going to try to make it so that there are more like, not section, I guess it would be sections. I don't know how they're going to do it like in terms of like the actual registration, but it's going to be like, I will have to teach the lab like 4 times in a row instead of once, each with fewer people, so that we can social distance. But it'll be the same total number of students for the class. That's what it looks like it's going towards. So apparently moving everybody from their part A instructor on to part B with the same instructor is something that they do frequently. And it seems like if there's not some sort of a special way for that to do, for a way to do that in terms of like giving you a special link or special registration window or something, what normally happens apparently is that, you know, you get the section number, just you register for the section number with my name on it. And ideally, all the students that took a particular instructor for part A would register for that instructor in part B. And there wouldn't be any like crossing over to like be stealing spots from other students. And even if that happened, I would probably at the very least add you guys. But I don't even know, I wonder how much control I have over like booting those people out. I don't know, but I would definitely add you guys. And I can't imagine that it would be so huge that it would be a problem. But maybe I'm just naive and optimistic. I don't know. I just think that
that's all of us trying to be optimistic.
Yeah,
it's gonna be fine. It's gonna be great.
It's gonna work. We're gonna make it happen. We're gonna make it. I really think that worst case, you'll get stuck with another instructor, but I'm gonna do everything in my power. And you guys, you know, you can get in touch with me if you try and register and there's a big problem. And if I find that there's like 10 of you that somehow couldn't get into my section and wanted to, but then there was like 10 strangers that had jumped ship from another instructor. This is like worst case scenario. I'm just like spitballing here. But if that were to happen, then I would probably go to Monica and be like, hey, here's a situation. Like, I'm willing to work another section, or is there like, how many people can I add, you know, and still do social distancing? We would figure it out. So stay in touch with me. You have my email. And we're still gonna be in touch for the next week at least, depending on when we decide to do our final. And I'm gonna send that poll out after today so that you guys can see the material and decide how much time you want to work on it. So yeah, that was really all that I had for you guys in terms of announcements. Make sure you study with your Wiley Plus stuff this weekend. It expires on Monday. It was free. It was good while it lasted. We'll have it again in the fall, and it will be integrated into Canvas, and it'll be very nice. But we're coming to a close on it for this semester. So this kind of stuff. But like the Wiley Plus adaptive practice, the quizzes, these interactivities. Make sure that you look at those this weekend, because that's going to be your last chance. Okay.
What about our lab grades? Mine hasn't changed.
For the exam, I'm still working on them. Sorry, yeah, give me until tomorrow night. I'm still working on them. They have been getting past me. Lab exam regrade. I probably have regraded, honestly, probably like 6 of them at this point. So I have a lot to get to. So I will work on that tonight and all day tomorrow, and then I'll have them done by tomorrow, probably tomorrow afternoon, honestly. Thank you for reminding me. That is a thing. I have to do your guys' quiz 12 and make a poll for you guys to find out when you want to do your final exam. There is a discussion now for special senses. If you haven't seen that yet, check it out and ask your questions there if you've got any, and I'll post any kind of like fun stuff that I found. I found some info on why we have melanocytes in the iris, which was kind of interesting. So check that out if you want to. And in our module for our last week of lecture, week 13, I added obviously our lecture video linked to YouTube to that, but also one more link to, oh gosh, week 14, where this is it, you guys, to the crash course video on vision, which is quite excellent, actually. So check that out. That's a really good resource for vision. There's one for hearing too, so I'll post that one as well down here. And we're going to continue this lecture using the same PowerPoint, right? We finished all the eye stuff on Tuesday. It was long, it was grueling. We survived. The video survived in its entirety, and it's up. So we are on slide 65 of 115. So it's actually, I think it looks like maybe a little bit less than what we did on Tuesday, but it's still gonna be a lot. So hold on to your butts. Here we go. Any last minute questions before I dive in here? Okay. All right, you guys, last lecture of the semester. Woo! Homebrewed iced tea. Okay, so the only two special senses that we're going to talk about this semester is your eyes and vision and your ear, which is hearing, but also balance, right? Your inner ear has to do with balance and equilibrium, right? So what we talk about today, we'll have to do with hearing a lot, and it's going to seem like it goes on and on and on, and then you're going to think that we're done, but then we're not, because then we need to talk about balance in the inner ear. Okay, so get ready to be looking for that second wind on this one. Okay, the external ear, the middle ear, and the internal or inner ear are the three parts of the hearing and balance apparatus of your body. So what we're going to talk about all three of those from external to internal, okay? Your external and middle ear are both involved with hearing. It is your, did I say middle? I said middle, right? External and middle ear are involved with hearing. It is the inner ear only that is involved with equilibrium and balance, okay? So there is a little, like the very tail end of hearing is there, but balance is only part of your inner ear, okay? And then external and middle are only hearing. Your hearing sensors, receptors, and your balance receptors are, they're different cells, and they respond to separate different stimuli and are activated independently. So it's not like you have ear cells that detect hearing and also balance. They're completely different mechanisms with a completely different whole set of structures and cells involved with them. So yeah, let's start on the outside with the external ear, shall we? We've got the auricle, or the pinna, which is the cartilaginous, fleshy part of your ear that you can see from the outside, right? So it's got all of these cool indentations and shapes, and it's shaped just very specifically so that sounds, particularly from in front of you, hit it and get bounced into this external auditory canal, okay, which is the part of the external acoustic meatus, right, which when we talked about the bones of the skull, we learned is this like tube-like channel through the temporal bone, right? So the external auditory meatus is the name of the channel that goes through your skull. You may also see your auditory canal, acoustic canal, external auditory canal, external acoustic canal. You might see all these different names for basically your ear canal, okay, which is part of your external ear. Your external ear extends all the way out here from the auricle, the pinna, all the way in to the tympanic membrane, which is your eardrum, right? In terms of the auricle being the upper part, the helix being like the outer edge or rim of it, and then the lobule being your earlobe. Those are all part of the ear that you can see from the outside. But your external ear extends in through the external acoustic meatus and ends at the tympanic membrane, which is the fancy anatomical term for your eardrum, okay? The tympanic membrane. Your middle ear is just past the tympanic membrane to the end of this ossicle, right? So when we talked about bones, cranial bones specifically, we did learn about the 3 little tiny ear bones or ear ossicles, and we're going to talk about those guys in a much more detail today. So this is your middle ear right here. And then your inner ear is all of this really weird stuff happening just on the other side of this window that your stapes is blocking right here. So from the tympanic membrane to what we call the oval window that the stapes is blocking is the middle ear, and then the inner ear is everything from the oval window on, basically, okay? So let's talk more about the external ear, or let's look at this image because this is out of your textbook. So this is the actual image for ear anatomy from your text. It is on page 658 if you're following along in your physical textbook. So on page 658, just another depiction of your auricle with the helix and the lobule, the external auditory canal or external auditory meatus, which is specifically the passageway through the temporal bone right here, and the tympanic membrane as the external ear. There's your little middle ear with your 3 ossicles, and your inner ear with all of this really weird snail shell, weird tubes kind of situation happening here. A lot of cool stuff happens in there. Talk about it in a minute. Okay. All right. The auricle or pinna includes the helix, which is the outer rim, and the lobule, which is the earlobe. And the external acoustic meatus or auditory canal is a short, relatively short, curved tube lined with skin. There are hairs in it. Most of the time they don't grow out of your ear, but sometimes they do. And then of course sebaceous glands associated with those hair follicles, and ceraminous glands, which produce ceramin, which is earwax, which is super duper important for catching stuff and or critters that might go into your ear, right? We want those things to get caught in the earwax and work its way out instead of getting to these delicate structures further on the tympanic membrane, but also in the middle and the inner ear. They say not to use Q-tips to clean your ear, and I also recommend it, even though I don't follow my own advice. It just feels too good. If using a Q-tip to clean your ears is wrong, then I don't want to be right. You know, it just feels so good. But note that when you do that, you are going to be inevitably shoving earwax a little bit deeper into your ear canal, probably, which can affect your hearing. It can actually cause you to produce more earwax, which sucks. And of course, you can end up poking your tympanic membrane, which is the worst case scenario. You really, really super duper don't want to do that. It will heal if it's a minor injury, but if it's a major injury, that shit will never heal, and then you will have hearing problems for the rest of your life. So be careful. Be very, very careful if you're using Q-tips in your ear, okay? All right. That eardrum, the tympanic membrane, is the boundary, again, between the external and the middle ear. It's actually connected on this side over here, on the inner side, to the first ossicle, to your first little ear bone, which is the malleus. So the malleus is going to be basically receiving the vibrations that your tympanic membrane receives after they are after those sound waves are shuttled into your external auditory canal after bouncing around in your auricle, right? So sounds come in, they're pressure waves in the air. They bounce around in your auricle. They get bounced into your external auditory canal, and then they basically like shake your tympanic membrane. And so that sound wave that was once a pressure wave through the air becomes a vibration. It's like another transduction of energy, right? A sound wave being translated into a vibration. And then that vibration is felt by these three bones in turn, which then vibrates another membrane here. And then this is actually your organ of hearing back here in your inner ear. So pretty cool. That's the basic pathway from a sound wave coming in, hitting the tympanic membrane, and then causing a vibration that passes down the malleus, the incus, and the stapes, and then basically gets turned into what is another pressure wave inside the inner ear, which we'll talk about shortly. But a lot of interesting transduction from one like energy type to another here, which is cool and interesting, and might remind one of your vision, in which you turn light energy into a electrochemical signal in the form of an action potential, right? By your photoreceptors, taking that light energy from the sun and then transducing it into something else, a different type of energy that it can share with the bipolar cells and the ganglion cells to send that back to the brain. And then that's what the brain interprets as a visual input. So got something kind of analogous happening here, which is pretty cool. Okay. So again, it's the boundary between the external and middle ears. It transfers sound energy from the external ear into a vibrational energy to the bones of the middle ear. And it is made of connective tissue, so it's not very well vascularized. So again, if you damage it, it's going to be very, very slow to heal if it heals at all. So be careful. I mean, yeah, be careful. And again, it revibrates in response to sound. Okay. Any questions about the external ear so far? Feeling okay about that? So far, so good?
Yeah, it's fine.
Pretty simple. Okay, moving into the middle ear. So the middle ear is actually a hollow space, even though it doesn't really look like it so much from this image. This image over here shows it more like a hollow space, but this is the Pearson version. So it is an air-filled cavity. It is lined with a mucous membrane. Okay, so a mucosa. So it's nice and moist in there. It's inside of your temporal bone. Okay, so it's actually like a little hollow space inside of your temporal bone at the other end of the external auditory meatus, right? So external auditory meatus, and then you've got this little hollow space inside the actual temporal bone right here, which is where your little ear bones, your ossicles, live. On the lateral side of your middle ear is, of course, the eardrum. And on the medial side, you're going to have it's going to be a bony wall with an oval window and also a round window. Okay, let me see, did I put this here? Oh, that's nice. We can nucleate that in a minute. Okay, so you've got the tympanic membrane on one side, and then you've got a bony wall on the other with like these little openings that lead to the inner ear, okay? And they're called the oval window and the round window, or technically the vestibular window and the cochlear window. Those will come into play later. Okay, above the actual ossicles, the actual ear bones, you have what is called the epitympanic recess. So epi as in above, tympanic as in your tympanic membrane or structures of hearing, recess, right? So it's like a little opening, this little space. So your epitympanic recess is up in here, where your little ossicles extend up into here. And excuse me, below, so this is going to be the what is above, what is above the ear bones, what's above the ossicles, and below the ossicles, you have a space that turns into a tube that actually goes from your middle ear into your throat. Okay, so actually sort of like the back of your mouth and throat. This tube, which is called in this text the auditory tube, which just seems odd to me since it's not actually a part of your hearing. I learned it as the eustachian tube, so you might see it also as eustachian tube. But in this text and in your text, it's called the auditory tube. That's fine. Just know that this is not actually like part of your hearing. Instead, this is actually going to be for equalizing pressure in your middle ear. So when you, if you dive, if you scuba dive, or if you snorkel and free dive, or if you go into an airplane and you're coming in for a landing, basically if you're going from a low pressure atmosphere to a high pressure atmosphere, you need to release the pressure. I think it's the opposite actually. You have to be going from a high pressure to a low pressure. You need to release the pressure from your middle ear. What I'm trying to say is there's these times when you plug your nose and you blow to open your ears, right? That pressure equalization, what you're actually doing there is you are, when you plug your nose and blowing, which is actually a little bit dangerous because you can mess up your tympanic membrane, but what you're gonna do, you can yawn, you can chew gum. What you're doing is you're opening up this tube right here and allowing the pressure that might have built up into in your middle ear to escape out that tube. And when you do that, you'll hear a pop or a crack, right? Because you can actually hear what's happening here. It will cause a vibration here, which you will then translate as sound in your brain. But since this middle ear region is basically water and airtight, if pressure builds up in here, then you're gonna be in a lot of pain. And if you've ever been on an airplane or dove or whatever, and you've had a head cold and this auditory tube is blocked up, you know the kind of pain that you can be in from the pressure building up in your middle ear here, okay? So does that make sense? The auditory tube leads from your middle ear. It's the only opening from your middle ear to it's your nasopharynx, so basically the back of your throat, behind your nose. And when you pop your ears, you're basically releasing that pressure. But when you do that, if you blow too hard and you blow air up into here, you can actually damage or injure your tympanic membrane, right? Because you'll be like blowing it out from the inside. So be careful when you do that. If you can do it by yawning or chewing, try and do it that way instead. But
I have a question, Miss Ashley.
Yeah.
So when like when water gets in your ear, like when you're in a pool, does that damage it doesn't damage it, but is that what the tympanic membrane
Isn't
is?
that interesting? I always wondered this because, okay, so your tympanic membrane it seals this opening, right? It's airtight, and it's watertight the way that I understand it. So since this is like a water and airtight region here, inside of your temporal bone, right, lined with mucosa, and the only way to release the pressure is to open your auditory tube.
Okay.
Then you would think that water coming in through your external auditory canal would like get to here and then not really be a problem. So when you do get water in your middle ear, which is what happens when you get an ear infection, right? You're gonna end up, what you probably did was you actually got water like up your nose, and it probably went up the auditory tube, and then you had water sitting in here. And then you had bacteria growing in that water that shouldn't have been there. So when you get an ear infection from swimming or something, it was from it coming up from this direction, and not coming in from actually going into your ears, because your tympanic membrane is actually physically sealing off your middle ear from the outside.
Oh, Okay.
Yeah.
It's kind of trippy because I kind of always figured it went in through my ears on the sides, not through my
I
nose.
know that's what you assume. That's what you assume, right? Yeah, but the middle ear it's like an enclosed space. The only opening to it really is this tube right here, because the oval window that this bone, the stapes, is blocking, it's sealed by the stapes right there. This window is actually sealed by a membrane as well, and then the tympanic membrane, of course. It actually seals that opening all the way around. So there isn't any way for water to get into the middle ear from out here. It has to come up from over here. Yeah.
Well, now I don't have to smack my head when I get out.
Right? Kind of crazy. Yeah. I mean, and so like what I want to know is how like eardrops and stuff work, right? Because if you're putting in eardrops,
You assume it's going all the way.
Yeah, you're putting them into your actual external auditory canal. So whether it's because there is a certain amount of penetration that happens, like just in terms of like maybe it just sort of soaks through the tympanic membrane, or maybe a little bit of fluid does soak through the tympanic membrane and it's not allowed to escape or something, it makes me think that it's not actually a watertight seal, because if you take eardrops or something, then that's gonna, obviously you're not taking it by like trying to get it up your auditory tube somehow by sucking it up your nose or something. So yeah, there's definitely more going on there, and I'm curious to find out now too.
Yep.
So like, how do eardrops work?
Because I would figure
I know. I want to know, man. How do eardrops work? Made myself a note, so I'm gonna put that in the discussions too. We're gonna find out what the deal is with that, because I do that all the time, at least for like, or like for earwax or any kind of like a little earache or something. Put like hydrogen peroxide in there and let it work, and it seems to work. So I don't know why, if it's something to do, maybe it's because the infection is on this side a lot of times, or the infection is actually associated with the tympanic membrane itself and not with the middle ear, or if infection can happen, any which way, and they just treat it according to the most likely cause first, and if that doesn't work, maybe you do something else.
Yeah.
I'm very interested to know.
When I have those aches, I don't treat it with eye drops. My mom taught me this thing because she used to do it to us when we were little. She buys marijuana and then lets it dry, and then soaks it in alcohol, and then puts in cotton balls, and then you put it in your ear.
As in like bud, like cannabis buds?
Yeah, so she lets it dry it out, and then she crushes it when it's dry, and then she soaks it in alcohol, and then like a few days later she puts cotton balls in it, and she puts it in her ears, and it goes away. And
okay, so you're soaking the alcohol that you made the tincture. It's like you made a tincture from cannabis leaves. You soak cannabis leaves in alcohol.
No, it's like actual like buds of marijuana.
Yeah,
but you just soak it in the alcohol. That's right.
Soak it in the alcohol, and then you stick it in your ear, or you soak the cotton ball in the alcohol and stick it in.
Well, my mom puts like a bunch of cotton balls and just lets them in there, and then whenever you need it, you just rip it. So there's a lot of people that just dip it and then just put it in their ear, but my mom lets it soak in there until like it lasts.
For ear infections.
Yeah, and then that's what we use on my niece all the time, and it always seems to cure her because my niece always has ear problems.
Well, like
and that's what I do now.
And kids especially. So the auditory tube in children, when you're developing, is more horizontal. So that means so water and stuff, when it gets in there, it doesn't drain out as easily. As you get older, it goes more vertical, so it drains more easily. So that's why kids are always getting ear infections, and hopefully you don't get as many when you get a little bit older. But that is like the coolest herbal remedy that I have ever heard, and I'm super into like herbal remedies.
Yeah.
But that's
and
really
I don't buy eardrops. I just do that, and I have some in my cabinets right now. And that's why my boyfriend always gets some, and I'm like, just go into the cabinet and get it and put it in your ear.
Dude, we need to take a step back and start looking into. I'm taking.
Actually, I have a question.
Into it. Yeah, go for it.
Do you know where it occurs when people have like a nasal drip? Because I know my sister-in-law tells me like, oh, the doctors say I have a nasal drip, and she constantly gets ear infections because of it.
Oh, interesting. So the way that I understand a postnasal drip has more to do with the nasopharynx. So where this actually leads to is like behind your nasal cavity, right? So everything behind your nose, it leads down the back of your throat, right? So when you have like a tickling cough from a nasal drip or something like that, it's because there's actually like mucus from your nasal cavity is dripping down the back of your throat and causing the tickle. So if it does, so that the auditory tube opens back there nearby, very nearby. So yeah, if fluid worked its way back there, or if you've got for some reason like an overproduction of mucus from this mucosa or something that was like trying to drip down the auditory tube but maybe couldn't, you can end up with an infection here, or just that excess of moisture could just be like a place for bacteria to grow and you end up with an infection that way. But I always thought that a nasal drip had more to do with having like a tickly cough because it's dripping.
Yeah, she gets that too, but she was telling me that like occasionally she'll also get ear infections, and then
That's
I guess the doctor said they're combined, but that makes sense.
Oh,
I'll take it.
I wonder if it's just like, I mean, does it have to do with like allergies or stuff?
I'm not sure. I'm not sure if she has allergies.
Thing, you know, like, I mean, when you get allergies and stuff, it's because then you're in your nasal cavity, which is also lined with a mucosa. It overproduces mucus and it'll give you that stuffiness. It gives you the runny nose. It gives you the postnasal drip. And then since this is lined with a mucosa as well, I would suspect that it could also overproduce. And then if you have a problem with your auditory tube where it was just maybe a little bit narrower than usual, or if it was blocked for some reason, especially if you just got other stuff going on, fluid stuff happening, then yeah, I could see there being like a backup up in here that would basically lead to a little bit of fluid that doesn't go anywhere, and so it just sits there and becomes a little breeding ground for bacteria, which is an infection, but by definition.
Oh, it's crazy how now we could start putting things together and start seeing it now that we know more and more.
It's the best!
Like we can make connections now.
I know, it's the best. It's so cool. I know, I'm excited for part B too, because there's more. I love talking about like the urinary system. It sounds crazy, but I feel like your kidneys are so cool. It's really cool. Anyway, getting way ahead of myself, like months ahead of myself. The middle ear, to continue, unless there are more questions. Any other questions? Okay. All right, so your middle ear, these three bones, your ossicles, right? They are the malleus, the incus, and the stapes. We introduced them back when we talked about cranial bones. They are suspended in their little cavity in the temporal bone by ligaments, and they actually are joined by synovial joints in between them. And since they're synovial joints, then we know that they are highly movable, right? So you've got like these highly movable little joints in between each of these three bones, and they're suspended all in a row by ligaments inside of this cavity. So you can see these suspensory ligaments here, 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 and here. So they're kind of like hanging. They're caused to be hanging inside of here. And that's because you don't want anything to be impeding the vibration that they're supposed to be sensing from the tympanic membrane, right? So when the tympanic membrane vibrates, it's going to first cause a vibration in the malleus, which is touching it directly. And then that synovial joint to the incus is going to cause the incus to start vibrating. Basically, the vibration is going to be passed down from bone to bone. So from the malleus to the incus to the stapes, the synovial joints in between each bone basically allows the vibration to pass through freely, right? And then finally, the stapes is going to vibrate, which is going to cause a little movement in the oval window that it's blocking here, okay? So the whole idea is that you're transmitting a vibratory motion from the eardrum to the oval window, and you go through three bones to get there. Tensor tympani and stapedius muscles. Don't worry about having to name these, but just know that they do help you in terms of being like a buffer system against super loud noises. Okay, so if you have a super loud noise, if you're at a concert or something, you're not wearing like earplugs or something, we're all guilty, right? And you are exposed to super loud noise, this muscle and what would be this muscle if they didn't chop it off right there, they will actually contract to keep the vibration from being from going out of control, basically. So if you had too much of a vibration coming from here, you don't want it to go all the way to the oval window, because past that you have some very, very delicate structures that could be damaged, and that would permanently damage your hearing, to damage the structures in here. So these muscles are going to help to keep the vibrations at a reasonable pace. Obviously they can be overpowered, right? Because people damage their hearing all the time. So they do a little bit. They're able to help you a little bit, but don't count on them. Okay, so this view is really weird. I didn't even know if I wanted to include this, but if you look at this next slide first, I feel like it might make a little bit more sense. So this is basically the same view as this. So you're looking at it from, I guess it's technically an anterior view, right? So you're looking at this person's face is here, and you basically did a frontal section like this through the ear, and you're seeing, so you get to see all the ear structures through here, right? If you were to rotate this image to where you were looking down the ear canal, okay? And not even that, you're gonna be rotating it literally the opposite direction to where you're looking out through the ear canal. Does that make sense? So it's like you're looking from the brain and looking out of the ear, okay? That's what you would be looking at right here. So you are situated, where we are is in the inner ear, okay, in the direction of the brain. And if we look out, if we're looking out towards the auricle, then you would see the other side of the tympanic membrane over there. It's actually kind of a neat view, because then you can see how it's sealing up that middle ear all the way around. You can see how it's attached to the malleus, the incus, and the stapes. And then we can see this end of the stapes that's blocking the oval window, right here in front of us. Does that make sense? It's kind of a strange view, but it also is kind of interesting and neat. You can also see the, there's another word for it that's not eustachian. So we're calling it the auditory tube in your text. That's this. You may also see a pharyngotympanic tube, as in leading from your nasopharynx up to your middle ear, right, where your tympanic membrane is blocking it off. So that's what this view is, right? So you're looking out from the inner ear. And then this one's a little bit more of a normal view, what we're used to seeing. That frontal section again through the ear, so that we can see this is the external auditory canal culminating in the tympanic membrane. We can see the middle ear nice and easily. We've got the malleus, incus, and stapes. The stapes blocking off the oval window and the round window right down here. The your auditory tube, right? Pharyngotympanic, eustachian, whatever, auditory tube. What else? Anything else happening in the middle ear that we should know about before I move on? I think we're good. All right, so if we carve the path one more time, just to beat a dead horse, because this is important. This is the pathway of sound, right? You're going out from the external environment, right? It hits the auricle or the pinna of your ear. It's going to bounce around in all of this interesting shape that you have in your ear, and it's all very, it's unique to an extent, but it's also evolved specifically to channel sound waves into your external auditory canal. It travels through the external auditory canal and it hits the tympanic membrane, okay? End of external ear, done. Your tympanic membrane vibrates from that sound wave hitting it. That vibration is caught by the malleus, which vibrates. Then the incus vibrates in turn. And then the stapes vibrates in turn. So we've turned this sound wave, this pressure wave through air going into the ear, we've turned that into a vibration motion, a vibratory motion, right? And that vibration motion happens all in the middle ear, passing through these 3 bones. When the stapes vibrates, it's going to also vibrate the membrane that's covering the oval window, okay? Which seals that opening to the inner ear, okay? So this is where we're at now. The stapes vibrating against the oval window, which leads to the inner ear. So let's talk about the inner ear now, okay? The inner ear is also known as the bony labyrinth because it's so weirdly complex and like maze-like and labyrinthian, right? Tortuous, I think that's a little bit dramatic. Is that supposed to be like torturous? Like I've never seen that word used in that context. Channels, again, this is still in the temporal bone. So this is all so small that it's happening, that it actually lives within the temporal bone itself, inside of little openings in the temporal bone. There are actually 3 parts to your inner ear. And remember, only one of those is actually involved in hearing. The other 2 are involved in your balance and equilibrium, right? So we're still talking about hearing now. We're going to get to balance and equilibrium in a little while because the hearing fun has only begun, okay? So the 3 parts are the vestibule, the semicircular canals, and the cochlea, okay? Vestibule, semicircular canals, and cochlea. The cochlea is the part that's involved with hearing. The vestibule and the semicircular canals those are both involved with balance and equilibrium. But all 3 of them are filled with a fluid called the perilymph, okay? Peri as in, well, remember how the paramecium is like the middle layer. It's not the epimecium on the outside of the muscle. The paramecium is sort of like inside. So peri is sort of like middle or inside, but not innermost. Lymph, like the fluid that fills your lymphatic system, okay? The perilymph fills the entire bony labyrinth of the internal ear. So all of those weird, freaky structures that we see of the inner ear, the snail shell, and all of these, the semicircular canals and stuff, all of that is actually filled with fluid. It's full of perilymph, okay? Perilymph. And the perilymph actually fills membranous sacs within the bony labyrinth. So when I say bony labyrinth, I mean literally. This is the hollow places carved out inside of the temporal bone, okay? So you can't pull the inner ear out and it's not gonna look like a piece of bony structure, okay? What we're talking about in terms of the bony labyrinth is actually like these hollow spaces carved out of the temporal bone, on the inside of the temporal bone. Does that make sense? These spaces inside of the temporal bone are shaped really weird, and they have these membranous sacs inside of them, and the perilymph is actually inside of those, okay? So the perilymph is inside of these sacs that sort of follow the shape of these hollow spaces that are shaped in these weird canals and stuff that are like boring through the temporal bone. And if you were to like inject wax or something into these spaces, then you would pull out something that looks like this, okay? That would be made of wax, but it's really just a hollow place that's shaped like this. I hope that makes sense. Okay. Okay. Oops, I misspoke already. Here we go. So the bony labyrinth is filled with perilymph, okay? And these membranous sacs that are inside of these hollow spaces of the labyrinth, the sacs themselves, those guys contain the endolymph, which of course is the innermost, okay? So you've got perilymph, in the space, in the gap in between the temporal bone and the membranous sac. And then inside of the membranous sac is endolymph. Sorry, I misspoke for a second back over there. Does that make sense to everybody? Did I lose anybody with that? Perilymph between the bone and the sac, but inside of the sac is endolymph. Is that okay?
Yeah, it makes sense.
Okay, cool. Thank you. Awesome. Okay, this is a really nice picture. I hate to walk away from it. Maybe I'll just name these things for you. We're going to talk about all of these structures here. Let me get my face out of the way. Okay, so remember 3 parts. 3 parts for the inner ear: vestibule, semicircular canals, and cochlea. The vestibule is really like this. It's like this first part. You can kind of see a little ghost image of the stapes covering the oval window here. Okay, so that's where the middle ear leads into the inner ear, is actually right here at this like bulbous opening here, which is called the vestibule. And the vestibule is kind of like the base for the semicircular canals over here, as well as the cochlea over here. Okay, so the snail shell is the cochlea, and the vestibule itself, as well as the semicircular canals, right, are part of your equilibrium and balance structures. And then the cochlea is just for hearing. So you've got all the rest of, this is the end of our hearing thing, and it's really, really cool how it actually works inside of here. There are different parts, of course, to all of these, and we're going to talk about them all. So we're going to talk about all of these different things here real quick. Oh, and this is reiterating what I was saying before. Hopefully I didn't confuse you. The bony labyrinth, which is just the hollow place inside of the temporal bone, is full of perilymph. And then you have these membranous sacs that are inside of the bony labyrinth that are full of endolymph. So the endolymph is actually inside of this pink structure here and this orange structure here in the cochlea. Okay? Okay, before I get too far ahead of myself. Okay, so the vestibule, since it's the base, we'll start there. It's technically part of balance and equilibrium, but the vibratory motion that has traveled down the malleus, the incus, and the stapes, in terms of from being a sound wave, is going to first enter the vestibule. Okay, so let's talk more about what's inside the vestibule a little bit. So it's, again, the central egg-shaped cavity of the bony labyrinth. It's basically like this whole part right here. It's continuous with both the equilibrium side and the hearing side, the semicircular canals and the cochlea. It is full of perilymph, and then these pink sacs are full of the endolymph. These pink sacs that I just mentioned have names naturally. How annoying, right? They are the saccule and the utricle, okay? I don't know. Oh, it says. Okay, so this is the saccule. This is supposed to be the saccule. And which one is supposed to be the utricle? Okay, so the big one is supposed to be the utricle, and the little one is supposed to be the saccule, okay? These guys are involved with balance, okay? So not hearing, so we're not gonna talk about them in any depth yet, or in terms of how they work. I'm just telling you because they're inside of the vestibule, which is this egg-shaped part right here, which is where the vibration from the stapes is going to enter the inner ear, okay? Okay, so the saccule is associated with the, make sure I get this right. The saccule is associated with the cochlea, and the utricle is associated with the semicircular canals. Okay, so that's how you're gonna tell those apart. Both the saccule and the utricle have equilibrium receptor regions called maculae. We're going to talk about them more in a little bit, but they are not going to be stimulated by this vibration, okay? They're going to ignore this vibration because it doesn't have to do with them. It has to do with sound. These guys, these maculae inside the saccule and utricle, respond to gravity and changes in position of the head. So again, these guys are involved with equilibrium, not involved with the sound wave that is coming in the form of a vibration here through the stapes, okay? So these guys are gonna sit here while we talk about sound, and then we're gonna get back to them when we talk about equilibrium and balance, okay? So when the stapes vibrates against this oval window, it is going to disturb what's inside of the vestibule. And that's as far as the vestibule is really concerned with hearing, okay? Once again, the bony labyrinth part of the vestibule, so everything around the saccule and the utricle, is perilymph, right? So you've got perilymph filling up this vestibule. And when the stapes basically like pushes against the oval window like this in terms of a vibration, it's actually going to cause a pressure wave. But instead of it being a pressure wave through air, like the original sound was, now it's a pressure wave through fluid. Now it's a pressure wave through the perilymph, okay? So that pressure wave in the perilymph is going to be shuttled down into the cochlea. And it is that pressure wave through that fluid and the fluid of the endolymph that is going to actually be interpreted as sound by your sensory cells in the cochlea and your brain, okay? Okay, so here's another view of the inner ear. The stapes again, here blocking off the oval window. The vestibule, this large like base opening for the entire inner ear. The saccule and the utricle here. And we've got this whole space. Yeah, this space is going to be full of the perilymph. And then inside of here, you're going to have the endolymph, okay? So when this stapes vibrates against the oval window, it's going to cause a pressure wave through the fluid right here. And then that pressure wave is going to travel all the way into the cochlea, oops, which is actually a coiled tube. So that pressure wave is going to travel all the way down that coiled tube, round and round and round to the end, and then back again, and then exit the round window, which seems crazy, but it's gonna. Let's look at them a little bit more closely. Oh, we're gonna talk about the semicircular canals briefly. So let's talk about, oops, I keep touching my screen, sorry. Okay, so let's talk about the semicircular canals briefly. These guys over here, once again, equilibrium, not hearing stuff. We're not doing hearing stuff here yet. We're talking about these strange rings. Hey, there we go. And there are 3 of them. And each one of those corresponds to a plane in our 3 dimensions, right? We are 3-dimensional beings. We evolved in the 3rd dimension, right? Out of who knows how many, right? And so we evolved to have 3 semicircular canals so that they can tell our body where we are in our 3-dimensional world, right? So one of the semicircular canals is going to be like going this way, one is going to be going this way, and one is going to be going this way, right? Just like the 3 planes of the body, right? The frontal plane, the sagittal plane, and the transverse plane, right? So those 3 planes are the 3 dimensions that we know as humans. And so they basically cover all 3 of those dimensions to tell our brain where we are in space, which is pretty awesome. Okay, so the ducts, which are these rings, there's like little hollow rings in the temporal bone. They, of course, have a membranous sac inside of each of them. It's in blue in this image. These ducts, these rings, these canals are going to communicate with the vestibule to a certain extent, right? Because the vestibule is continuous with them. Keep firing. And inside the base of each of these rings, right here, you've got like a little bulbous base at the end of each ring, are these ampullae, which are very similar to the ampullae that are inside of the saccule and the utricle of the vestibule, but they detect, they work slightly differently. They actually have a very specialized structure, which we're calling the equilibrium center, which is called specifically the crista ampullaris. So the cristae ampullari, plural, are going to be these little purple guys in this image, okay? So the ampulla is this bulb at the base of this semicircular duct, and inside of the ampulla is a crista ampullaris, okay? So these ampullae are all contain cristae ampullari. Okay. And these receptors respond to rotational movements of the head, right? So that's movement versus just position. And we'll get more into that. Still has to do with equilibrium and balance, just a slightly different form of it. Okay, all right. I'm really excited to follow this pressure wave of sound so that we can understand where sound comes from and how our hearing works, okay? So the cochlea, again, is the snail shell down here. It is continuous with the vestibule, right? The saccule and the utricle are also in the vestibule, but they're not concerned with sound at this point. The vibration that comes in through the oval window via the stapes is going to cause a pressure wave through the fluid, the perilymph fluid in the vestibule. And that pressure wave of fluid is going to travel down into the cochlea, which is a hollow tube, which is coiled around itself, okay? So the cochlea itself, a spiral, conical, bony chamber, so it's a hollow place inside of the temporal bone, again. It extends from the vestibule, it's continuous with the vestibule, even though it's involved with hearing and the vestibule is involved with equilibrium. It coils around a bony pillar, which is called a modiolus, which is very similar to like an actual snail shell. If you've ever seen like half a snail shell or a broken snail shell, a dried out one, if you've ever seen a broken one, you can see that there's actually like a bony pillar on the inside that the spiral goes around. Kind of like the central pole around a spiral staircase, right? Most of the time, most spiral staircases don't go around nothing. They usually go around like a central pole. That tube that is coiled on itself is called the cochlear duct, okay? So we call this tube the cochlear duct. And inside of the cochlear duct is a super specialized, very, very, very small organ called the organ of Corti, or the spiral organ of Corti, whatever combination of those things. The spiral organ of Corti is the most complete, so I guess I'll just use that. But I might abbreviate that to spiral organ. And that spiral organ of Corti ends at the cochlear apex, which is the pointy outside end of the snail shell, right? So it's like here. Okay. There will be more pictures to make this clearer, okay? So don't panic yet. So the hollow inside of the cochlea is actually divided into 3 chambers. So that tube that I'm talking about has like 3 sections in it. So it's actually like 3 tubes bundled together inside of 1 tube, okay? They are called the scala vestibuli. They're each called a scala. I'm not sure what scala means, but they are called the scala vestibuli, the scala media is in middle, which is technically the cochlear duct, which contains the endolymph as well as that spiral organ of Corti, and the scala tympani, okay? The scala tympani and the scala vestibuli are continuous with each other at the cochlear apex, which has a special name, and that is the helicotrema, which is actually super fun to say if you want to try it. The helicotrema. So let me go back to our other picture here real quick before I do that. So again, this snail shell is called the cochlea. Inside of it, it's a bony, it's a hollow place in the bone, the temporal bone, right? But it's full of a membrane called the cochlear duct, a endolymph-filled membrane called the cochlear duct. The cochlear duct is technically only one tube inside of this greater tube, which is actually kind of like 3 tubes bundled together, okay? Let's look at this other picture here. Might make more sense. If we were to take the snail shell and like unspiral it, right? Uncoil it, because right now it's all coiled up. If you were to uncoil it all the way down like that, then you would see the cochlear duct. So this one tube going right down the middle. And then you've got a second tube above it, which is the scala vestibuli, and a tube below it called the scala tympani. Then if you did a cross section right here, you'd see that there's 3 tubes, okay? 1, 2, 3. When I say that the scala tympani and the scala vestibuli are continuous with each other at the helicotrema, what I mean is that where the pressure wave starts and goes down the scala vestibuli, it goes all the way down that coiled tube to the apex, which is represented right here, and it actually turns around the end of the cochlear duct right here and becomes the scala tympani, okay? So the scala vestibuli and the scala tympani are continuous with each other because one basically turns into the other at the very, very end, at the apex of the cochlear duct, which is the one in the middle, which just ends here. It's sealed off right there. Does that make sense? Sort of.
Yes.
Okay, cool. So you basically have like 3 tubes in one coiled structure that looks like a snail shell. The scala vestibuli is the basically like the first length of the tube. So it's one of 3 tubes basically, but it's basically the first place where that pressure wave that came from the vibration of the stapes is going to go down first, down the cochlea, okay? So the vibration of the stapes turns into a pressure wave in the perilymph. This is perilymph in here, okay? It actually is going to be starting in the vestibule. This image is a little bit oversimplified because remember, this is more accurate in terms of the structure, right? So the vibration of the stapes translates into a pressure wave in the perilymph in the vestibule, and that pressure wave is going to go down the scala vestibuli in the cochlea, okay? So from here to here is simplified right here, okay? So the pressure wave of fluid is going to travel down the scala vestibuli all the way down to the end. When it turns this corner at the helicotrema, which is the fancy name for this apex of the cochlea, it will turn into this scala tympani, okay? And then that pressure wave will continue down the scala tympani until it hits the round window, which is that other little membrane covered window that is in the bony wall of the middle ear. And basically all that little round window does is the membrane in it just goes boop, and it just kind of like pooches out. Boop. It kind of like catches that pressure wave and gives it some place to go. So basically just the pressure wave comes all the way down and hits it, and this round window sort of pooches out a little bit and then goes back. And then that's how you kind of like absorb the energy of that pressure wave when you're done with it. Okay? I'm gonna just continue to dig into this a little bit. Hopefully it'll continue to make more and more sense. Okay, so if we look at it in terms of this image here, you can look at it in terms of like this being the upper duct, and then this being the lower duct. So the scala vestibuli is like the roof or the upper duct, and the scala tympani is like the lower, what are they gonna call it? The floor of the cochlear duct. So this is kind of like in terms of the actual cochlear duct itself, which is the duct in the middle, which is full of endolymph and which terminates at the helicotrema. Okay, so this is the cochlear duct is in the middle of all this. Okay, so it's in the center of this tube, but it's enclosed in itself. It's like its own little enclosed thing basically in the middle of this tube, a tube within a tube. And above it, it seals off, and above it, you've got the scala vestibuli, and below it, you have the scala tympani, okay? So you can look at it in terms of the scala vestibuli being the roof of the cochlear duct because it's above it. And you can look at the scala tympani, why do I keep saying scalar? Sorry, the scala tympani as being like the floor of the cochlear duct, okay? And I know that this is kind of weird how the cochlear duct looks like it's pink and yellow. That's because this pink part is the actual hollow tube that is full of endolymph. The yellow part is supposed to be that the spiral organ of Corti, okay? So it's this actual organ of hearing is in yellow right here, okay? All right, bear with me. So the roof of the cochlear duct is the vestibular membrane. The floor of the cochlear duct is the tympanic membrane, but between the two, you've got the basilar membrane, which is, the floor of the cochlear duct is the scalar tympani, but between the scalar tympani and the spiral organ of Corti, right, this pink line right here, you've got the basilar membrane, okay? It's here. So it's this pink line separating the spiral organ of Corti in yellow from the scala tympani right below it, okay? So the basilar membrane is an actual membrane, and it's super important because it actually is where your actual sense of hearing is sensed, so to speak. Okay. We're going to talk about the cochlear nerve here in a minute as well. Okay. So here's another picture. This one is from your text, as was the one of the middle ear. Excuse me. The one from the middle ear is on 659. This image is a couple pages down. We're looking at figure 17.21 on page 662 now, 662. And we can see again the end of our stapes. Here's our stapes in the middle ear. So the middle ear is like out here towards us. Here's the stapes covering the oval window. There's the round window, and on our side, we're in the middle ear, right? So there's a bony wall in between basically the stapes, which is on our side, and all of this inner ear stuff is on the other side of that bony wall, okay? The stapes and the oval window lead into the inner ear at the vestibule, which is this like pear-shaped, egg-shaped thing, this blob right here, which contains the two membranous sacs called the saccule and the utricle, okay? These guys are involved in balance and equilibrium, as is the system of tubes called the semicircular canals, right? And these semicircular canals are continuous with the utricle. They have their own little sensory centers inside of their little bulbous bases right here, okay? But when a sound wave traveling through air hits the tympanic membrane, vibrates the ossicles, and reaches the oval window, that vibration of the oval window gets translated into a fluid wave in the perilymph that is in the vestibule surrounding the saculonutricle, and that wave, that pressure wave through the perilymph is instead going to be forced down here into the cochlea. So here is the scala vestibuli, and these arrows are showing the direction of that pressure wave through the perilymph. It's going to travel down the scala vestibuli all the way, here it is again, all the way down to the helicotrema at the very end here, and then it's going to turn the corner and become the scala tympani and come all the way back around until it hits the round window, which is going to pooch out a little bit to basically release the pressure of that wave. In the middle of the scala vestibuli and the scala tympani is the cochlear duct. So you've got the tube down the center with the scala vestibula above it and the scala tympani below it. The cochlear duct ends at the helicotrema, and it contains the spiral organ of Corti, which is your actual organ of hearing. Okay. This one is a continuation of that same image on page 662. This is really cool. We're getting some really cool stuff here now. So here is the oval window. I don't know why it says stapes in the oval window. This just looks like the oval window with the stapes removed, but whatever. In the vestibule, and so the pressure wave travels down the scala vestibuli, which would be this one, which travels all the way around. And you can see in this cross section of the cochlea that this is supposed to be like the bony pillar that these tubes are traveling around. Okay, so basically it's like a hollowed out tube in your temporal bone that's like spiraled all the way up to the helicotrema at the end, and then all the way back down again to the round window. This is your cochlear duct. Okay, so it's this little duct sandwiched in between the scala vestibuli and the scala tympani. Okay, and inside of the cochlear duct, you've got this funny little thing. We're looking at it from a distance now. It looks like a little tongue or something, a little flap. And that little flap is the spiral organ of Corti. We're kind of like sneaking up on it now, okay? Let's sneak a little bit further, see how close we can get to it, okay? All right, so if you took like one of these, basically this squared box, excellent. This box, and you zoomed it in, boop, you would see this, okay? So this is basically a little chunk of your cochlea where you can see a little section of your scala vestibuli, your scala tympani, your cochlear duct sandwiched right there in the middle, and oh, there it is, this, the spiral organ of Corti. So here's that little flap that you kind of could see before. And you're starting to get a little picture of like the little cells and stuff that are involved with this, okay? So just to reiterate, again, sorry if you're getting tired of it, but the pressure wave through the perilymph is, it's basically traveling down the scala vestibuli, so like, oh, like say away from you in this picture, okay? So it's like traveling down away from you, down this tube, goes all the way to the helicotrema, turns around into the scala tympani, and comes back until it's coming out towards you from here. So that pressure wave would be returning from here along the scala tympani. As that pressure wave passes through these tubes, they are going to inevitably disturb the membranes in between themselves, in between this tube and the cochlear duct, right? So as that pressure wave is passing by right here, it's going to disturb this membrane, which is going to disturb the endolymph inside the cochlear duct, which is going to disturb the spiral organ of Corti. And it's that disturbance, that the spiral organ of Corti, the disturbance from the pressure wave passing by up here, that is going to be translated into an electrochemical signal that goes down a nerve to your brain, which is translated into sound. And then as the sound comes back through the scala tympani, it's going to disturb the basilar membrane right here, which is also going to disturb the spiral organ of Corti, right? So we're kind of sneaking up on how this actually works, right? It's kind of cool. So if we zoom into, again, this box, I really love when they do this. So page 662 and 663 of your text is a really neat sort of like large expanded view or large view, and then we're kind of like zooming in and zooming in and zooming in, and we do that 3 times. It's kind of neat. So the final time is to zoom in on this box and specifically on the spiral organ of Corti itself. And remember, this is a little section of it. It's a long, skinny thing that basically sits along the bottom of the cochlear duct, right? Which is spiraling all the way through the cochlea to the helicotrema. So this is just a little section of it. So we're looking at a little slice. This is just a little slice of the spiral organ of Corti. And let's zoom in on it a little bit and see what we got here, okay? All right, so it's weird. It's totally weird. This structure, the weird flap structure, is the tectorial membrane. Think of it like kind of like tectonic plates on the earth, right? That's the thing that's actually going to move, right? That's the thing that's actually going to be disturbed when a pressure wave passes through the scala vestibuli above it, in the tube above it, right? So it's surrounded, it's surrounded by endolymph here, and then the scala vestibuli is above that, and the pressure wave is going through the scala vestibuli and disturbing the endolymph that this guy lives in the cochlear duct, and then it's going to cause this tectorial membrane to move, right? And when this tectorial membrane moves, it's going to tickle these little hairs, or stereocilia, a very specialized type of cilia, on these super specialized sensory cells called hair cells. And they're called hair cells because they have this special stereocilia that sticks up out of the top of them. And it is the stereocilia that's embedded inside of the tectorial membrane, so that when the tectorial membrane moves, the stereocilia move. And when the stereocilia move, that's the signal for this hair cell to depolarize, right? So it's going to allow positive ions to flood in and send an action potential out down its axon, shoom, which all gathers into one, kind of like the optic nerve traveling out the back of your eyeball. It's going to gather to become the cochlear nerve, right? Or specifically, it's the cochlear branch of the vestibulocochlear nerve. And the vestibulocochlear nerve is the big, fat nerve that ends up leaving your inner ear to go to your brain. And so you have a branch from the cochlea called the cochlear nerve, or the cochlear branch, and a branch that comes from the vestibule. So the branch that comes from the cochlea is carrying information regarding sound, and the branch from the vestibule is carrying information regarding balance and equilibrium, okay? How do you guys feel about the spiral organ of Corti? Any questions about this so far? How are we doing with this? It's really weird, right? It's pretty wacky, but cool. Wacky, but cool. Does it make sense what I'm talking about when I say that the pressure wave is disturbing? I keep doing this. When I say the pressure wave through here is disturbing the endolymph in here, which disturbs this tectorial membrane. Does that make sense? Then the tectorial membrane, when it moves, it's going to move these little stereocilia, or cilia, excuse me, that are up, like sticking up into it from these hair cells. And when it moves, those little stereocilia get bent. They kind of get moved around a little bit, right? And depending on how much bending they experience, that's basically like the frequency of the sound that your brain is going to interpret. So if it's a really loud sound, then this is going to move a lot. It's not the frequency, but the actual, the loudness of the sound. So if it's a really big or loud sound, the pressure wave traveling up here and down here will be very, very strong it will cause a great disturbance in the endolymph here and cause the tectorial membrane to move a lot. And if these little guys get bent a lot, then they're basically going to send a stronger signal that depolarization is going to be very, very intense, or it's going to happen very, very frequently to tell your brain that it's a louder sound. The frequency or the pitch of the sound that you're hearing, that depends on where along the spiral organ of Corti that sound wave is actually going to be disturbing the hair cells. So if you have a high-pitched sound that you're hearing, that sound, I've got a better one here. Here we go. Back to this guy. Make sure that I get this right. Did I not have the key? Oh, cool. This is from your text as well. This is on page 664, and it comes with, or it's right next to the key with all of these numbers and what they actually correspond to up here. So make sure you check that out on page 664. Basically, what I want to make sure that I get right here is whether or not this is a high-pitched or a low-pitched sound. Does it matter? Is it not saying? Oh, various frequencies cause certain regions of the vestibular nerve vibrate more intensely than other regions. Okay, so it has to do with, so the frequency of the sound and the pitch of the sound has to do with whether or not that the pressure wave, the resulting pressure wave, is slow or very, very fast, but also if the pressure wave is felt, basically the spiral organ of Corti along its length has hair cells that are specialized, basically like tuned in to particular pitches of sound. So if a pressure wave passes through the scala vestibuli all along here, and it has a certain, if the sound associated with it, this vibration has a certain pitch associated with it, it basically won't be read by the hair cells until it reaches a certain point, until it reaches the hair cells that can actually like perceive it, okay? So basically the frequency, the loudness, and the pitch of the sounds, all the sounds that you hear have to do with how strong the pressure wave is, how long the wavelength between waves is, so how slow the wave is, how long and slow the wave is for usually like a lower, it would be a lower frequency sound, versus very, very high frequency sound with lots and lots of fast waves coming, and where that wave is detected along the spiral of Corti, or the spiral organ of Corti. So if the spiral organ of Corti detects a sound wave here, the hair cells that are associated with that little section of the spiral organ of Corti are going to be triggered. They're going to send their signal to the brain via the cochlear branch of the vestibulocochlear nerve. And your brain is going to say, okay, this is the frequency of the sound, this is the pitch of the sound, and this is the loudness of the sound. And all of that information together allows us to hear things, okay? Which is pretty insane. It's so complex, but kind of beautiful in its own way. So you can disturb the basilar membrane by coming through the scala tympani, or you can disturb the vestibular membrane by coming down through the scala vestibuli. And depending on which section of the organ of Corti this is, it will basically respond to that stimulation or that disturbance in the endolymph or a disturbance in the basilar membrane, according to like where it is and according to the pitch and frequency of that sound. Yeah. Okay. Any questions about sound and hearing? I know it's a lot. It probably takes a bit to like formulate some questions. But that's basically how it works. And I kind of went into this a little bit, got ahead of myself. So sound is actually a pressure disturbance, right? So it's a wave. So alternating areas of high and low pressure. So like the crest of the wave versus the trough of the wave is the high pressure, low pressure, right? So basically is like traveling through the air or traveling through any fluid, right? Air is considered a fluid, and the perilymph and the endolymph are considered a fluid as well, but it's just a pressure wave produced by a vibrating object. So it's produced by a vibration. And a sound wave moves outward in all directions from its source, right? And it's illustrated by an S-shaped curve, right? And I talked about, well, frequency. I should probably understand more about like what pitch actually means. I guess it just has more to do with like the vibration of the source. But the frequency in terms of like the physical property of sound waves is the number of waves that pass a given point in a given time. So like a high frequency would be many, many waves in that period of time. And a low frequency would be fewer waves in a given point of time. The wavelength is the distance between one wave and the next. So having a low frequency would correlate with having a long wavelength, and a high frequency would correlate with having a short wavelength. And then the amplitude, which is the actual loudness, is the actual height of the wave. So the wave can be either very, very big or very, very small. And that has to do with the loudness of the sound. Okay. Oh, and here's a picture of that. So if you had something like a tuning fork, which would be your source of sound, here's basically the waves, which is basically like these blue dots are particles of air. So it's basically like shoving these air particles into like a wave-like formation. The same way that kind of like wind does for the ocean or for a lake surface of water, right? Creates waves. So the wavelength is the distance between the crests of two waves. The amplitude is the height of the wave. And the frequency is how many waves go by in a given period of time. So how fast the waves are coming. What else? So to recap one more time, the sound waves vibrate, well, they vibrate from their source. They travel through the air, the fluid that is the air atmosphere that we live in. They hit your auricle or your pinna, bounce around, get channeled into your external auditory canal. They hit your tympanic membrane, which vibrates. And then the malleus vibrates, the incus vibrates, and the stapes vibrates. And it amplifies pressure at the oval window. So as the vibration travels from one bone to the next, it's actually amplified a little bit. So by the time it hits the oval window, it's very strong. So once it hits that oval window, you're then basically initiating, boom, a pressure wave through now perilymph, okay, which is like more of a liquid fluid, a liquid wave. So waves below the threshold of hearing travel all the way around past the helicotrema and back again and leave through the round window. No harm, no foul. It's not perceived by us. Our little spiral organ of Corti can't hear it, can't sense it, can't perceive it. So that's why certain sounds are either too high for us to hear or too low for us to hear, right? Sounds that are in the hearing range will go through the scala vestibuli first, which in turn disturbs the endolymph in the cochlear duct, which vibrates the basilar membrane. It vibrates I want to call it tectonic membrane, but it's not, the tectorial membrane, or the basilar membrane underneath it as it goes by through the scala vestibuli or the scala tympani. And once that happens and the spiral organ of Corti gets activated, it will be vibrating it at a specific location. So the basilar membrane is literally just the part of the spiral organ of Corti that vibrates when a sound wave is passing through the scala tympani underneath it, right? So when the basilar membrane gets disturbed, again, the hair cells are going to get bent and depolarize. And according to the frequency of the sound, that will happen somewhere along the cochlear duct, somewhere along the spiral organ of Corti. So here's another image. This is not from your textbook. This is a Pearson image, just their version of that image that's on page 664 in our book, showing the pathway of sound. So tympanic membrane, ossicles, scala vestibuli, also the cochlear duct, and then the scala tympani, right? So basically this is a sound within hearing range, and this is a sound that's not in hearing range, okay? So a sound in hearing range is going to be felt or sensed at a certain point along the cochlear duct or the organ of Corti, and a sound that's not within hearing range is going to keep going all the way around and back out. And the pressure wave caused by sounds that are audible will also inevitably need to go through the round window at the end too. But the sounds outside of your audible range are just going to go right past without being sensed at all by the organ of Corti in the cochlear duct, okay? Everybody okay with the pathway of sound?
Yeah.
Yeah, it kind of makes sense. It's really complicated. Read the section in your textbook. That'll help, and I'll also post the crash course video on it as well. So that will probably break it down.
Go back and just like relook. I just re-see the video and it makes sense, a little more sense.
Yeah, the more times you look at it, the more it'll start to sink in. It's a lot of information right now. So I just wanted to point out that these are all the axons of those hair cells, right? That get depolarized at whatever region. So basically, if the frequency of the sound makes it discernible right here, then it's going to disturb the hair cells in the organ of Corti right here, and those hair cells are going to depolarize and send their signal down their axons right here. Okay, and then this is basically all of those axons from all of these different hair cells along the spiral organ of Corti and the cochlear duct. And when you put them all together, you get the cochlear nerve, or the cochlear branch of the vestibulocochlear nerve, which is what it looks like when you put it all together. Oh, this is cool too, but let me see if I can find, here we go. This is a really nice picture of that too. So this is just another way of looking at all of the axons of all of these hair cells bundling up together and leaving the cochlea through the cochlear nerve right here. And then the cochlear nerve is going to meet the vestibular nerve right here. And then you're gonna have the vestibulocochlear nerve, which is the combined nerve of these two bundles. I didn't even realize that I had this. This is nice. Okay, so again, the high frequency sounds are going to displace the basilar membrane closer to the oval window, and then the lowest frequency sounds are going to disturb the hair cells out towards the helicotrema, which is kind of cool. So everything in between is going to be somewhere along the in-between of those two extremes. Pretty neat. And this is because the fibers of the basilar membrane are actually structured differently. So you have short, stiff fibers at the base, which will only be moved by high frequency sounds. And then towards the helicotrema at the end, this image, if this is like freaking you out, this is the cochlea unraveled, okay? Basically like uncoiled into a straight thing. So you have the scala vestibuli up here, the scala tympani down here, and the cochlear duct right in the middle, right? So you've got a different structure in the actual fibers of the basilar membrane over here by the oval window than you do out here by the helicotrema. Out here by the helicotrema, you have long, floppy fibers that will be able to pick up low frequency sounds. Okay, so that's how it works. So it's pretty crazy. A nice close up of your spiral organ of Corti, your textbook version of this. I guess that would have to be the one on 663. This is a slightly different version just to give you a different look at it. So the tectorial membrane, the stereocilia on the hair cells, which are embedded in the basilar membrane. And when this basilar membrane or the tectorial membrane get disturbed, like this, it's going to cause those little stereocilia to bend. And then that causes the hair cell to depolarize, which sends the signal down the axon and out through the cochlear nerve to the vestibulocochlear nerve, which goes to your temporal lobe, to the temporal lobe of your brain, actually. Okay. All right, so there's a couple of different ways that you can have problems with your hearing. One would be what's called conduction deafness, which is when you actually have, when the vibration never even makes it to the fluids of the internal ear, okay? So basically you have a problem with either like earwax is blocking your external auditory canal, or you damaged your tympanic membrane, or your ossicles are somehow damaged and can't pass along the vibration. Whatever it means, it's before the oval window, okay? So a conduction deafness is a deafness because of something basically in the pathway of sound before the oval window. So you never even get a chance to have that pressure wave going through the scala vestibuli and scala tympani, okay? Sensorineural deafness, sensorineural deafness is basically the opposite. So that's going to be deafness that happens as a result of something going wrong inside of the cochlear duct. So it's happening inside of the cochlea. It's a problem with the hair cells themselves or surrounding structures in the organ of Corti. So if you go to a concert and you expose your ear to a sound that is too loud, and it travels through your tympanic membrane, through the ossicles, into your inner ear, and it passes all the way along the scala vestibuli to whatever point it gets perceived, and you burn out those hair cells at that particular point, that pitch, that sound, a particular pitch of sound, you can become deaf to. So that's why people can become deaf to high pitch sounds, high frequency sounds, or just low frequency sounds. My dad, he's a musician, and whenever he mixes music, he always puts in too much like cymbals, which is a super high frequency sound, because he can't hear it anymore, because he's exposed himself to really high pitched, high frequency sounds for too long. And he basically like has killed those hair cells at that base end of the cochlear duct of that organ of Corti, basically. So once those hair cells are gone, they're gone. They can't repair themselves. They don't regrow, nothing like that. You end up being deaf at whatever that little region is that gives you the perception of that particular pitch. So whenever he records, he ends up having to like just manually take down like the treble of whatever it is he's mixed, because he knows that he can't hear it, but it's probably too loud for everybody else. So sensory neural deafness is when you actually damage the hair cells themselves. So it's a neural problem, right? Sensory neural has to do with the hair cells, those sensory cells specifically, okay? You can also have tinnitus, right? Which is chronic ringing or clicking sounds in the ears without there actually being an auditory stimuli. Super annoying. I don't have it, but I imagine it must be super annoying, something to ignore. And that's just because of the actual cochlear nerve degenerating. So, or inflammation of either the middle ear where your ossicles are, or the inner ear. I didn't realize this about a side effect of aspirin that really super sucks. Aspirin is a blood thinner, so I wonder if that has anything to do with it. But yeah, it's basically the nerves are firing without being stimulated by an actual outside source. And Meniere's syndrome is a disorder of the labyrinth that affects the cochlea and the semicircular canals. So not only are you going to have problems with hearing, but if you have problems with your semicircular canals, then you're going to have like vertigo, which is going to probably cause nausea and then vomiting because your body thinks that you're in a spin, thinks you're spinning when you're not. So let's talk about how that might happen with the semicircular canals and such. Let's start again at the vestibule, right, which is the egg-shaped base of your inner ear where the oval window goes into, right? You've got the saccule and the utricle in there. And then you've got the semicircular canals coming out of it at the other end as the cochlea. So you got the vestibule, the cochlea down here, and the semicircular canals over here. The vestibule itself and the saccule and utricle inside of it have to do with a particular type of equilibrium that we call static equilibrium. Okay, so static equilibrium is literally like telling your head that it is, or telling your brain that you are, that you're moving, but not necessarily that you're like spinning. Okay, so it's more, it has to do with like gravity movements. So like up and down or side to side. So this is what's going to tell you that you're going up in an elevator or down in an elevator, or if you're like accelerating in a vehicle or decelerating in a vehicle, for example. Okay, so this is just up and down and side to side motions happening in the vestibule, the saccule and utricle. The semicircular canals, which again are correlated with the three planes of our three dimensions. Those guys are going to tell us about dynamic equilibrium, which is basically spinning and turning movements. So think about like, again, with those three planes in our third dimension, also can be, you can think about it in terms of like flying an airplane. You have like if the airplane, I don't know, if the airplane is like this. Okay, it looks like a Viper from Battlestar Galactica. Are there any other Battlestar Galactica nerds out there? Probably not. Oh well. Okay, so you've got pitch, right, like this. You've got roll, like this, and you've got yaw, like this. So basically, those three types of movements are the only three types of movements that we can perceive, and so they're each taken care of by one of these semicircular canals. And here they are again with this same image, 1, 2, 3 semicircular canals with an ampulla at the base, in this bulbous base, each containing a crista ampullaris, which we'll talk about more in a second. And the vestibule, which again, static equilibrium, up and down and side to side, or like horizontal, vertical and horizontal movements versus the spinning movements of like this or this or this. Okay. All right, so you've got maculae in your saccule and utricle in the vestibule. Vertical and horizontal movements. These maculae are the actual sensory receptors, and the way that they are structured is specific to, and the way that they're positioned inside of those structures is specific to what it is that they are needing to sense. So each, so you have one macula in the saccule and one in the utricle, in the walls of these sacs, basically. They monitor the position of the head in space, which is also necessary for us to control posture, so that we can tell if we're starting to, like, you know, fall asleep and droop and it wakes you up, you know, or if you're like falling over. This is all very important. They respond to linear acceleration forces, but not rotation. Okay, so again, linear as in either in a straight line up and down, or horizontal, parallel to the surface of the earth. They also have hair cells. So the hair cells in the cochlea are designed to interpret pressure waves into sound, actually pressure waves into a nerve impulse, basically. But these hair cells in the maculae of the saccule and utricle in the vestibule are designed to interpret these kinds of linear acceleration forces. They also have their hair cells because they have stereocilia, just like the ones in the cochlea. So they've got little stereocilia sticking out of the top of them. And those stereocilia and kinocilia, but don't worry so much about that, are also embedded in a gel-like membrane, kind of like the, I keep wanting to call it tectonic, and it's not. It's the tectorial membrane. So they also have a jelly-like membrane, like the tectorial membrane, that also helps them to bend according to the movement of that membrane. But it's very specific to this type of like sensory experience, okay? The way that the membrane moves is because the membrane has these little tiny rocks, these little tiny bits of like minerals embedded inside of the membrane. So it's those rocks responding to gravity that causes that squishy gel membrane to move, which then causes the stereocilia of the hair cells in the maculae to move. So let's look at some pictures of this. They're calcium carbonate stones, by the way, in case you're curious. Not something you need to know, just in case you're curious. So the utricle is involved with horizontal motion. So the utricle is going to be what tells you that you're speeding up in your car or you're hitting the brakes in your car. Okay, so this kind of horizontal, parallel to the Earth's surface kind of acceleration. Okay, also tilting the head side to side, but not rotating, but tilting. Okay. The maculae and the saccule respond to vertical movement. So basically it tells you if you're like when you're jumping up and down, or if you're going up or down in an elevator, okay? Or you're falling, like, you know, feet first or head first, it'll tell you that. Pretty important to know, but you know. In addition to your visual stimuli, you're gonna also need that in case you can't see. So here's what's happening inside of the macula of both the saccule and the utricle. The structure is the same. It's the orientation that's different, okay? So it's the way that they're oriented that makes them respond to gravity in such a way that they can basically respond to these two different types of linear movement. So you also have, so you've got hair cells, right? Embedded in like a base, which is actually the wall of the saccule or the utricle. And the hair cells have stereocilia, which are these hairs sticking out of the top of them. And they come up and they are embedded in this gel-like membrane, which is called the otolithic membrane, okay? So called because it's got all of these otoliths embedded in it. So otoliths, so lith is anything having to do with rocks, lithic. The otolithic membrane has to do with these little liths, these tiny liths, which are called otoliths. And if you are in the saccule, then say that you're in an elevator and you're going up, right? When you go up, the little otoliths in the otolithic membrane are going to like depress into the membrane for at least for a second, right? And that's that feeling of ooh, going up, is because those little otoliths are pressing down into the membrane as they're basically like fighting against gravity as you're going up. And that little downward pressure is going to be sensed by the stereocilia of these hair cells of the macula. And that is going to cause them to depolarize and send the resulting signal out to the brain through the vestibular nerve, right? The vestibular branch of the vestibulocochlear nerve specifically, okay? So that's what would happen in the saccule. In the utricle, this is like oriented in such a way that instead of gravity basically causing the otoliths to either sink into the otolithic membrane or kind of rise and pull out of it as they would as it does in the saccule, which is for up and down motion. Instead, since we're talking about horizontal motion with the utricle, these little otoliths are going to be like sort of like rocking one way or another, opposite from the direction that you're moving, right? So when you accelerate, if you're accelerating in this direction over here towards this, then as you accelerate, these little otoliths are going to be kind of like left behind for a second and sort of like pull on the otolithic membrane, and therefore pull on the stereocilia of the hair cells and cause them to depolarize and send their little signal to the brain saying that. And so your brain, depending on whether that signal is coming from the saccule or coming from the utricle, your brain interprets that as either an up motion, down motion, depending on whether or not these little hair cells are being pushed in one way or another, or a forward motion or a back motion or a side-to-side motion, whatever, a horizontal motion parallel to the surface of the earth. Yeah, so that's how you perceive static equilibrium. That's why you get that funny feeling in your stomach when you go on like Tower of Terror. It's not Tower of Terror anymore, but rides like that where you get dropped in a free fall. Or if you go up in an elevator, you get that little feeling. And that's your brain. That's those little otoliths sinking into the otolithic membrane for that moment and triggering these hair cells to depolarize and tell your brain, you're going up, we're going up. So that's pretty cool. So this is the mechanism for perceiving static equilibrium, up and down, vertically, or horizontal movements. Okay. Does that make sense so far? Static equilibrium? Doing okay with that? Any questions about that? So far, so good?
Yeah, so far so good. It's not that confusing.
It's not that bad, right? It's really neat. It's really cool how it works. It's amazing. Of course it's amazing. It's the human body. It is amazing.
Yeah, it is. It's interesting.
It's like it's so weirdly complicated and yet very elegant in the way that it works, because it can go wrong, and it does go wrong, but just the way that it's designed, you know, that you can't, it's just kind of beautiful. It's just kind of poetic the way that it works. Yeah. So again, bending the hairs in the direction of the, so basically there's a little bit more to it, but I'm not worried about these details. The actual specific direction that it's going to tell your brain is determined by whether or not the hair cells are being moved away or towards this special cilia called the kinocilium. Okay, so if this is the utricle and we're talking about horizontal motion, and if we're traveling in this direction, then the otoliths would pull the otolithic membrane and therefore the hair cells sort of in this direction away from the kinocilia, kinocilia. And so that specific signal, that specific stimulus in that very, very specific instance is going to cause the cell to depolarize a certain amount and tell the brain, okay, we have accelerated in this direction this much. So which way these hair cells or these stereocilia are bent in relation to the kinocilium and how much they are bent tells you the direction and the magnitude of the acceleration. Pretty amazing. So basically, the more that they are bent, the more that they depolarize, as in like sort of over and over again, you get that neurotransmitter being released. And you get, if you have a lot of neurotransmitter being released, then you have a big signal going out through the vestibular nerve. And then bending in the opposite direction basically polarizes it in a different direction. That's how those two signals are interpreted from each other. So you can have depolarization, as in you're making both sides of the membrane an equal charge. And then you can have hyperpolarization, which is basically making them the reverse charge. And those are interpreted two different ways by the brain. Pretty cool. So that's how your brain is informed of your changing position, right? And that in combination with your visual input, right? And sometimes even your audio input, right? Gives you all the information you need to know about where you are in space. And that's why, like, not being able to see or being in like a low light situation or a no light situation is all the more disorienting, or why being on the inside of a boat or the inside of a car and not looking out of the windows at the horizon can give you sickness, right? Can give you like car sickness or seasickness, because you're not linking the visual input with the input in your vestibule of your inner ear. And if those two things don't match, your brain is just like, what is happening? So it's like, according to your eyes, you're sitting still, right? Because you're looking at, your phone or the table in front of you, and it's like, okay, we're sitting still. But your inner ear is telling you, oh my God, we're rocking back and forth, or oh my God, we're moving fast, we're accelerating in this direction, or we're turning, and that's why you get car sick or seasick, because the visual input and the input from your inner ear don't match up. And so your brain thinks that something terrible is happening. And then you eject the contents of your stomach. Like, it's an emergency, quick, drop all the weight we don't need, I guess. Which is like kind of silly and sad, but we're just not really designed for that. And it affects some people more than others for whatever reason. My husband has vertigo on roller coasters, horrible vertigo on roller coasters, like inevitably pukes on roller coasters no matter what, but he has never once been seasick. I don't know, but I get seasick and I'm great on roller coasters, so oh well, I'll just take my Bonine or whatever, and maybe I should give him Bonine before we like go to ride roller coasters. I should try that. I wonder if he'd be into that. Probably not. Throwing up after a roller coaster is not fun. All right. So that's the static equilibrium. Oh, and here's another picture of that basically. Okay, so this is kind of cute. So basically, if you're tilting your head one way or another, the little otoliths in the otolithic membrane are going to basically like pull on the membrane by being pulled by gravity, right? In whatever direction they are. And the little stereocilia are going to be yanked in one direction or another. And how they're yanked in reference to that one kind of cilium is what's going to basically tell your brain or differentiate to your brain the direction that you're going. And the amount of bending is going to tell you like how fast you're going in that direction. Pretty neat. Okay, last part. Let's talk about our dynamic equilibrium. Okay, so let's talk about the semicircular canals. So at the base of the semicircular canals, remember, you've got these ampullae, and inside of those ampullae, you are going to have these structures called the crista ampullaris, or crista for short. The cristae ampullari, plural, are the sensory receptors for dynamic equilibrium, in the way that the ampullae of the saccule and utricle are for static equilibrium. Trying to figure out where we are here. Page 660, I just passed 667, and now I'm looking at page 668, I believe. Okay. So each one of these cristae has support cells and hair cells. Again, we're still working with hair cells. We still have the same like basic mechanism for the stimulus happening here, but because of where it's coming from and these hair cells, these specific hair cells, it's going to tell your brain completely different information than the hair cells in either the vestibule or in the cochlea, right? These are hair cells in the crista ampullaris. So it's telling you about dynamic equilibrium only. The gel-like mass that these hair cells are embedded up into is called the cupula, okay? There's a really nice image of it on page 668, and I believe I have it here in the next slide as well. Don't worry about that. Okay, oh, we're going back again, just kind of backing up a little bit to say what we're talking about. Talking about the semicircular canals, talking about the ampullae, and the crista ampullaria in each of those ampullae, which is basically the base, at the base of each semicircular canal, okay? All right. Okay, so here we are at the base of the semicircular canals. We're looking at the crista ampullaris of this particular one, and inside of that, you can see our little hair cells with their little stereocilia, and this time the hair cells are up here embedded in this really weird, sort of like flower bud shaped jelly structure, and it's called a cupula, and it's very bendy, and it kind of like, it can be bent in different directions like this, okay? So that's how those little hair cells are gonna be bent, right? Here's an actual electron microscope image of the cupula in an ampulla of a semicircular canal. Crazy, so crazy. Here's another picture. This is the one from your text. This is on page 668. So again, here we are in the ampulla of a semicircular canal or semicircular duct. I believe the semicircular canal is the word for the hollow part in your temporal bone. And the semicircular duct is specifically the membrane canal on the inside that's full of endolymph. So if you've got these little cupulas down here in the base of each of these semicircular canals, how is it that they become stimulated? Well, let me tell you. Your semicircular canals, the semicircular ducts, excuse me, specifically, are full of endolymph, right? Let's see if I can find another picture of that. Okay, so you can see the semicircular duct inside of the semicircular canal here in this picture, and our little ampullae are inside of the semicircular duct, right? So this is the membrane part right here that is inside of the hollow bony structure of your temporal bone. So you've got endolymph surrounding this entire structure. It's going throughout the entire semicircular duct, and it's surrounding the cupula in the ampulla, right? And it's all continuous, right? This is all open. This isn't closed off. This is open to the rest of the semicircular canal. This is open to the rest of the semicircular canal, semicircular duct, okay? So basically, with that endolymph surrounding this structure and being continuous with the semicircular canal, every time that you rotate, every time that your head rotates in space, whether it's with or without your body, right? So if you're just shaking your head no, like this, the semicircular canal in your inner ear that is associated with that plane, which is going to be this horizontal plane, right? That semicircular canal, semicircular duct, and the endolymph in it is going to be turning like this, right? If I took I want to take like a ring or something, I need like a rubber band. Maybe my watch will do. So if my watch is that semicircular duct, so it's a ring, right? If you turn it in the plane in which your head rotates like this when you're saying no, that semicircular duct is going to be spinning like this, right, in your head as you're doing that, which means that the fluid, the endolymph inside of it, is also going to move, and it's going to spin inside of that duct. So it's spinning, swirling, spinning around in there as you do that. And as it's swirling through that duct, it's going to flow past the cupula, And when it does that, it actually bends the cupula, which bends the stereocilii of the hair cells that are embedded up in it. So as your head rotates in that plane, in this direction, the endolymph spins, and basically it triggers the cupula of that particular semicircular canal, the one that's rotated or that's positioned according to that plane. It's going to trigger those hair cells associated with that cupula, which is going to send a signal to your brain that that semicircular canal is rotating, therefore your head is rotating in this direction, right? Same thing for spinning in your chair, right? For like if you just spin or something. If you're like on the zipper or something and you're like rolling forward or doing somersaults, the semicircular canal that's associated with that plane of existence is going to be spinning. And it's the endolymph inside of that is going to flow past the cupula at the base of that semicircular duct. And that cupula is going to then trigger its hair cells to depolarize and send a signal to the brain that you are spinning in this direction. And then lastly, right, if you're like doing a cartwheel, that semicircular duct is going to be spinning, its endolymph is going to be flowing past its cupula, and then its hair cells are going to send the signal that you are spinning in this direction all the way around, right? Pretty simple. Like it's actually it's pretty beautiful how that works, right? So your different cristae, the crista apularis, which again is this whole thing, right? It's the crista ampullaris inside of the ampulla. So this like weird bulbous structure is the ampulla, and inside of that is the crista. Those cristae respond to changes in velocity of rotatory movements of the head, okay? So not only does it tell you which direction you're rotating based on which cupula is being activated, but it tells you the velocity of that rotation based on how fast that endolymph is flowing, therefore how much that cupula gets bent by that flow of endolymph past it. So the bending of the hairs in the cristae causes the hair cells to depolarize, right, and send rapid impulses to the brain at a faster rate in the case of a higher velocity spin, right, and a slower rate for a slower spin, right? And then bending the hairs in the opposite direction, of course, is going to, instead of causing a depolarization, cause a hyperpolarization. You don't have to worry about these details. Depolarization is fine, but to tell the difference between like whether you're spinning clockwise or counterclockwise in whatever direction, it's basically whether or not it's a depolarization or a hyperpolarization that's happening to the hair cell. But either way, it's being signaled to, it's being triggered to send a signal down to the vestibular branch of the vestibulocochlear nerve to the brain. Thus, the brain is informed of rotational movements of the head. Cool, right? So here's another picture. If you're spinning, there's the cupula bending, and then as you slow and stop, the cupula is actually going to sort of overcorrect and bend in the other direction. That endolymph might actually like come back a little bit, and your brain can account for that. That's fine. As it slows, the endolymph keeps moving in the direction of the rotation, which bends the cupula in the opposite direction. Basically, your brain knows, it can interpret that, as long as it doesn't continue in this opposite direction, it can interpret that as a slowing and then an eventual stop in which it would look like this. It would come back to being straight up and down. Woo, that was it. We did it. That was the last lecture. All right, you guys. What did you think of that?
Not too bad.
Yeah. Did you really? So do you feel like vision was worse?
Yeah, I had to watch it like twice.
Yeah. The vision one, yeah, I guess the vision one there's just like a lot of names. There's a lot of names in this one too, but there's just something so exciting about it. It's just like,
I feel like with this one, it's easier to connect with what they do because they actually like connect with one another. With
like,
the eye, it's the same thing, but each one is still a little different.
Yeah, they each do their own specific thing.
Yeah.
So as long as you can keep like the names of the parts for each of these different systems, for each of these three systems, right? Because you've got the hearing system in the cochlea, the static equilibrium of the vestibule, which is the sacral and the utricle, and then the dynamic equilibrium of the semicircular canals, and all of their parts. If you can keep them straight, then you'll be golden. You'll be totally golden. And just like I said, I would write down or try and find something that says the pathway of light or the pathway of the signal for vision. I'll do the same for the pathway of sound for you guys, and I'll post those guys in the discussion. And then I'll put this video as well as the crash course video for hearing in the module for week 14.
Ashley, over the summer, I kind of don't want to forget any of this since I'm not taking any courses. And I was wondering, like, can we view your videos without a link on YouTube?
That is a really, really good question. I can't technically make them public since you guys didn't sign a waiver to have your images available on the internet. I was told this, it's a legal thing. But since you have the links now, I imagine that if you right-clicked on the link and copied it and then pasted it into like a Word document, you would have that link. Or you could just bookmark the page on I think, is it a channel? Can you guys are you able to actually see the whole channel? That's a really
Let me check.
I think you can only see that one video.
You see that one video at a time? Ah, that sucks. Ooh, maybe I can email you a link to the channel. I'll look into that. But either way, if you just save the links, as long as you have that link, you should be able to get to it.
I also had a question.
Yeah.
For for fall.
Yeah.
Would we need to know, well, we would need to have an understanding. I understand that, but
yeah,
we still need to remember all of this.
No, no, we're not going to revisit it in this class. I mean, this is introduction to anatomy and physiology, right? So this is like your first really kind of in-depth taste of it, but you'll see it again. You'll see it again in other anatomy courses. But yeah, we're going to move on to the other body systems. We're going to talk about the circulatory system and the digestive system and the urinary system and the nervous system. And we probably touch on these things, remember last semester with this thing and this thing, but I'm not going to you won't be tested on any of this stuff specifically. You'll be expected to have an understanding of it. I haven't thought about this, but I might need to resurrect certain terminology for you in the context of other body systems, because remember in the first, our first lecture, we talked about the human body. We talked about how all the systems, we talk about them in terms of the 11 body systems, but they're all interconnected, right? To maintain homeostasis, they're all talking to each other constantly.
Yeah.
So even though it's a different system, the circulatory system, we're going to be talking about certain tissue types. We're going to be talking about cardiac muscle, we're going to be talking about things that we have discussed before, and I might need to resurrect those terms and say, we're going to have to know this one again. So it's all interconnected. These super minute details, not so much. The general stuff, we're going to talk about depolarizations and cells for the nervous system and stuff, but the different parts of the inner ear, no. You might see them again if you become an ear, nose, and throat doctor.
Yeah, but I will still say the lectures because it's always fun to go revisit.
Cool. That's awesome. That's really good to hear.
Yeah.
Good to hear. I know that I ramble, and sometimes I stay too long on a thing and I talk and talk and talk and talk about it. And that's my one complaint really in student evaluations is God, move on. But I feel if you're the one that's waiting for me to move on and is bored, that's fine, but there's gonna be those students that need that extra reiteration. It doesn't hurt. It doesn't hurt you really.
Oh, no,
as much as it helps the ones that need that reiteration. So I'm still finding that balance. But yeah, hopefully the videos aren't too grossly long with me just rambling.
Yeah, for me, I don't even skip the videos on YouTube because it's the more you keep repeating it, the more I understand it.
Oh, nice.
sometimes I won't even like understand it, and then I have to go back to like 10 minutes when you started and then go again. I'm like, oh, okay, I see.
Good, good. I'm glad to hear that. I'm glad that it's not just like, okay, move on. That's good. Cool. So again, I will post this down here, and I will post the crash course video down here, and I'll see if I can't whip up some pathways for you guys. I'm gonna whip up a poll about the final exam and see what how you guys are feeling about that. Again, the earliest that it could possibly be would be next weekend, but that'll be up to you guys whether or not you want to just get it over with, or whether you want to hold off and have more time. I don't know what difference it makes for you on a like an administrative level to have the grade now, and if that's a thing, then obviously shoot for the earlier date. Maybe I'll give an option for in between as well, so that maybe we can see where you guys stand on that, because it doesn't really make that much of a difference to me. What else? I'm going to look into these questions that we discussed. I'm going to continue to regrade your lab exams. Your grades will go up, but I may not get to them until tomorrow. Bear with me. I'll see if I can get a link to the actual YouTube channel. I'm not sure if that's possible. And I'll email that to you. I'll do a recap email like I usually do. So yeah, anything else? I'll be back on Tuesday to do like a catch up or a review session. So this is not the last time you're gonna have to look at this face, sorry, but I'll be back in case you guys have questions. I'll be back at 5:30 too, but that won't be the last time either. So Tuesday we'll do a recap, not a recap, but I'll be there for your questions. And
so is next week when the final is gonna open?
The next week I have the lab final scheduled for Thursday, which is the 28th. And then our lecture final was scheduled for June 9th. So that's like a huge gap in between those two. So what I would like to do is have obviously both of the exams available at the same time as per usual. I'm just trying to decide when that time should be. And so I'm going to find out whether or not you want that to be the weekend of the 28th or the weekend of the 4th. Actually, that would probably have to be those two options. It would have to be the weekend after Thursday, May 28th, or the weekend after June 4th, because the weekend after June 9th, the semester is over and we can't have our final then anyway.
Yeah.
Yeah, so I'll give you guys those two options and tell me which you prefer. It'll be the same format, all the same format, open Thursday night, close Sunday evening. And then I have 5 days to input grades, so 5 days then to battle it out in terms of assignments, scores that you don't agree with and stuff like that. So getting those final grades input will be 5 days after whenever we have the final exam. It's gonna be 5 days after the last day of the final, whatever that is. So we've yet to find out what that will be exactly, but I will let you know as soon as I do the poll and give you guys a reasonable amount of time to respond. Give everybody a reasonable amount of time to respond to that. That sound okay?
Question.
Yeah.
Awesome. Yay.
Ashley,
Yeah.
I have a quick question. Are we getting a study guide for this final exam?
Absolutely. So that also depends on when you guys want to have it. So I'll start working on it either way in case you guys want to have it earlier.
Okay.
Study guide. But that will be something that I'll get to you as soon as possible, especially if you guys vote on next weekend. Vote to have it next weekend.
Okay. Thank you.
Yeah, no problem. All right, I'll be back at 5:30 in case you guys think of anything else. And I'll be emailing you later on. So thanks for putting up with this last lecture, and it was a doozy. This last week the whole week was a doozy, but it was super fun, and I'm here to help you out if you got lots and lots of questions about it, which I'm sure you will. So yeah, I guess I can stop recording.